Here's a question that decides how you retire. Two friends both put away the same money, a little every month, same amount into the same account. The only difference? One starts at 25. The other waits until 35. Same paycheck, same discipline, just 10 years apart. And by retirement, the early starter has almost twice as much. Same money in. Wildly different money out. The culprit has a name you've heard, but maybe never really felt: compound interest. Money that earns interest, and then that interest earns interest, and so on forever. It doesn't add up. It multiplies up. And the tool that captures exactly how it multiplies is one tidy little equation. Let's start simple. You drop some starting capital into the bank, call it K0. Each period, the bank bumps it up by a rate P. So next period's balance is just this period's balance, times 1 plus P. That's the whole rule. One step at a time. Apply that rule again and again, and the pattern jumps right out. Each period multiplies by the same factor, 1 plus P. So after n periods, the balance is K0 times 1 plus P to the power n. That's geometric growth, the exponential curve everyone draws when they talk about the magic of saving. But real retirement saving isn't one lump sum. You start with an empty account, and every single month you add a fixed amount, call it A. So now, going from one month to the next, two things happen at once. The old balance earns its interest, and you toss in a fresh contribution on top. Write that down and you get this. The next balance equals 1 plus P times the current 1 plus A. Move things around and there it is, a linear difference equation of first order but with a constant A sitting on the right. That constant is what makes it non-homogeneous. And it's exactly what makes it interesting. Here's the strategy, and it's the same one that cracks linear differential equations. The full answer splits into two pieces. One solution of the homogeneous version, the equation with a 0 on the right, plus any one particular solution of the real thing. Homogeneous handles all the possible shapes. The particular one just nudges it up to the right level. Take the homogeneous piece first. Set the right side to 0, and every term is just a constant multiple of the one before it. That's the fingerprint of a geometric sequence. Guess a solution of the form c times g to the n, plug it in, and the g pops right out. G equals 1 plus p. So the homogeneous solution is c times 1 plus p to the n. Now the particular piece. Since the thing forcing the equation, the contribution A, is just a constant, we guess that the particular solution is a constant too. Call it alpha. Plug a constant in, the two alphas combine, and you're left with minus p times alpha equals A. So alpha is minus A over p. That's the whole particular solution. Snap the two pieces together, and the general solution is c times 1 plus p to the n minus A over p. Now we pin down c using the fact that the account starts empty. At n equals 0, the balance is 0. Set n to 0, and c has to equal A over p. And just like that, everything is nailed down. Put c back in, tidy it up, and out drops the punchline, the future value of an annuity. The accumulated capital equals A over p, times the quantity 1 plus p to the n, minus 1. Look at what it's saying, your money grows exponentially with the number of periods, and that little factor A over P just scales the whole thing by how much you save and by the rate. And this is where it gets genuinely startling. Picture a bar for every year. The blue part is the money you actually put in. It climbs in a boring straight line. But the green part, the interest on the interest, that grows like a rocket. Early on, almost everything is your own deposits. Decades later, most of your wealth is money the account earned for you. That's the whole reason the person who started 10 years earlier wins so big. One last twist, for when interest is credited more often than once a period. There are two honest ways to split a yearly rate across, say, 12 months. The conformal way keeps the total growth identical, 1 plus p sub m, all to the m, equals 1 plus p. But the proportional way, just dividing p by m, quietly gives you a little more each time, and by Bernoulli's inequality, more compounding beats less. Push it to the limit, credit continuously, and that factor climbs all the way to e to the p, the bank constant. So the lesson is the same one that opened this. With compounding, when you start and how often it compounds quietly decide everything.